Thank you very much, Judd. Again, my name is Juan Velasco. I am the Marine Pollution Program Lead at the Satellite Analysis Branch, which is at the NESDIS office of NOAA. I have a background in molecular biotechnology and also GIS and remote sensing. And this is my first time at this workshop. And now that I've seen today's presentations, I feel like I could have been a little more technical with my presentation, but I'll remember that for the next time. So I'll just give a brief overview of how we use optical and SAR satellite imagery from polar orbiting sensors for marine oil spill detection. Okay, so our program became operational in 2011. It was started to assist the Office of Response and Restoration in monitoring U.S. waters for a natural oil spill emergencies. We started development before that in 2009, 2010, and we were also involved in creating products for the Deepwater Horizon spill. So that gave us a good way to work on producing this product. So what I mean by unnatural oil spills, I mean accidental and intentional oil spills, such as those caused by things like oil platforms, oil pipelines, and other oil infrastructure. Also illegal discharges from ships and oil leaks from shipwrecks that are classified as environmental threats. NOAA maintains a database called the Roulette database where they track sunken ships that pose potential environmental threats based on the contents that they contain. SAB analyzes satellite data and reports marine oil spill to stakeholders at the Emergency Response Division at NOAA, the U.S. Coast Guard, BSEE, as we've heard mentioned all day, the Bureau of Ocean Energy Management, and other federal and state offices involved in emergency oil spill response. Our main oil product is called the Marine Pollution Surveillance Report, or MPSR. Our products created since March of 2018 are public and are available at our website. And I'll provide the address to that at the end of the presentation. So we use both types of available remote sensing, remote sensing types, the passive and active remote sensing. So the passive remote sensors collect solar energy reflected by the Earth's surface. For oil spill monitoring, we mainly use the reflected visible and infrared wavelengths. The Landsat and Sentinel-2 missions are examples of polar orbiting passive sensors. We don't use geostationary sensor data like those on board the GOES satellites for meteorology, because the resolution is too coarse to see oil spills. Something really large could probably be seen, but not with enough detail to actually make a usable product. So we don't use that. In contrast, active remote sensors, they emit their own pulses of energy, and the sensors measure the reflection of that energy. Interestingly, oil spills reflect very little energy back to the sensor, and we'll see why that is in a moment. A radar system like synthetic aperture radar, or SAR, is an example of an active sensor system. The attenuation of surface waves by oil slicks cause specular reflection. When a SAR sensor sends energy pulses to the ocean surface as seen in A, the oil surface reflects the pulses away from the sensor, making the affected area appear dark since the energy did not get reflected back to the sensor for recording. When a passive multispectral sensor captures solar energy reflected from the surface as seen in B, oil that lies in sunglint, will appear bright, while oil not in sun glint will appear dark. If the sun is located either too far from nadir or the point directly below the satellite, due to the season, open ocean waters will be too dark as well, making oil spill detection difficult there. For those who aren't familiar with it, sun glint is just a phenomena that occurs when the sun glint reflects off the surface of the ocean at the same angle that a satellite is viewing the surface. In the area lit by sun glint, smooth ocean water becomes a silvery mirror, while rougher surface waters appear dark. So here's an example of an optical imagery image capturing an oil slick. The arrow is pointing to the location of a Deepwater Horizon spill, or at least the origin. And then the silvery feature that goes up and down the left half of this image is the actual oil spill itself. Because it is located in sun glint, it's silvery because the light is illuminating it, and so that's how the oil appears in sun. And as I move away from the sun's path toward the right of the image, the oil starts to get darker, and at some point it's just not visible once you get too far to the right. And that's what the circle is supposed to reflect here, that oil just became darker here. Some of the darker features could also be related to rough surface conditions. And here's an example of lots of oil off of Southern California near Santa Barbara. So this area is full of natural oil seeps. So there are always slicks present there. That arrow on the upper left shows a small linear slick extending south from a natural oil slick, which is indicated by the orange circles. And the same down here in the lower right. And Sentinel-1 is a SAR image, so as I'm sure most of you are familiar with, it's a black and white image, a grayscale image, excuse me. And the circled area captures kind of a messy area. There's a bunch of natural seeps located there, and some of these linear features are related, but there's also a lot of natural phenomena. Some of the larger masses of dark could be related to a combination of oil mixed with low wind conditions that caused specular reflection in those areas. So a radar return was not achieved. Also, dark features could be caused by upwelling as surface winds blow water horizontally. Cold air from the bottom rushes up to replace it, and it causes wave dampening on the surface. So that also produces a dark feature. And here's an example of a report that we did in 2020 from an anomaly off the coast of Southern California. It's a dark feature, as we would expect oil to be. It also has some indication of some effect from the wind, as it causes some streaking in portions. And also it's a shape that we wouldn't expect to see naturally. If it was connected to a natural oil seep, we would expect to see something linear. But something like this is not the shape of something that would be caused naturally. And that's why it was reported. So SAR sensors and optical, they both have their advantages and disadvantages with regards to oil spill detection. The advantages of SAR sensors is that since they use radar and they're not dependent on clear skies or time of day. Different SAR sensors have different wavelengths, and depending on those wavelengths, they'll allow them to see further through deep cloud cover. And time of day, so it doesn't matter what time of day it is, because oil will be on the surface. It will reflect the signal away from the sensor, and clouds will not be an issue. Also, because of the longer wavelengths, there are minimal atmospheric effects. Someone that is familiar with working with optical image processing, for example, knows that before you can really pull some information out of the image, you have to clean it up. You have to do some processing to correct atmospheric effects. Well, that's not the case so much with sensor data. And also, SAR sensors are capable of imaging in different modes. So depending on the size of the spill or the amount of detail that you like, it's possible to select modes that'll satisfy your requirements. If you have a really big spill, you can get a mode that will take a larger footprint of the area. Or if there's something that you want to see in greater detail, you sacrifice the size of the area, but you get better resolution. So it offers some flexibility. The one major disadvantage of SAR data is that it's only one wavelength. So there's no way to create a false color composite, for example, if you wanted to rule out some vegetation, for example, such as in the Gulf of Mexico and off coast of Florida, there could be a lot of sargassum beds that in optical could look like oil slicks because they're brown and linear. But you can't test for that with SAR data because there's only one wavelength. And there's no way to make a color image, and much less a false color image using near infrared, for example. And optical sensor advantages are that we can see oil colors. We can see details about a slick if we have a true color composite available. We can also derive some information about the thickness itself, not how thick it is, but just different colors, different sheens. And also we can rule out false positives because we do have access to more bands. We can make false color composites and rule out vegetation, for example. The disadvantages of optical sensors for oil spill detection is that they're dependent on clear sky conditions. If clouds are present, they won't be able to see the oil. And this is really a challenge when we have hurricanes that go through the Gulf of Mexico, in which we have to wait a few days for the hurricane or tropical storm to pass before we can get a clear image of the surface to see if any oil slicks began or were produced because of a passing storm. Also, optical sensor data is not useful when sun glint is not present. So for instance, this time of year here in the Northern Hemisphere, the sun is still pretty far south. So if I have an image in the northern latitudes, there's a good chance I won't be able to detect any oil in it because deep ocean water can be dark. It'll be dark blue or black, and I won't be able to pick out a slick with it in that area. And lastly, a disadvantage is a daytime data. So reflect kind of ties into the sun glint. Is since we use only visible bands and near infrared and not thermal, for example, I can only use daytime data to analyze. I should mention that all the analysis that we perform is done manually. So we have programs that'll retrieve the data and unpackage it for us, but all of the analysis is done by hand. Okay, SAB also takes part in assisting with the collection of satellite data for oil spill research. Between 2015 and 2017, NOAA and BESI coordinated in situ studies and satellite imaging strategies to gain an understanding of oil thickness characterization with high resolution optical satellite data. Phase one of the study involved the release of hundreds of gallons of crude oil at onset. SAB assisted by coordinating the collection of high resolution data such as Worldview 2 and Worldview 3 to image onset at the time of those in situ thickness and emulsion measurements. And phase two replicated those thickness and emulsion measurements at an active spill site in the Gulf of Mexico, so in open ocean water. And the images on the left are two worldview images of the onset tank. You can see, although they don't provide a lot of detail, the tank is still pretty small in the image. It's really the value of that the pixels themselves contain that are value. So in these images, there was enough pixels available of the oil spilled in the tank to be useful. And then the image in the upper right just shows the vessel that was on site. I believe Oscar Garcia Pineda, who is also giving a presentation this week, was on board taking measurements along with colleagues. And also the resolution shows that even a passing airplane was visible. And here's an example of a report that we did with thicker oil and the rest of it. So as a result of that study, we started to identify relative oil thickness in optical satellite data beginning in 2018. Our map products only distinguish two general thickness types, thicker oil and the remaining oil, but differentiating between them is becoming increasingly difficult with the higher resolutions of nascent satellite sensors. That is because data is now showing much more slick detail, making it difficult to separate a slick into thickness types, particularly since spilled oil is defined by varying colors and sheens. We have silvers, whites, metallics, browns, and so forth. The accident spill site here is in the Sentinel-2 image. It was caused by an oil facility, and we identified the relative thicker parts of the oil as a silver or whitish areas surrounded by the thinner black oil. But even here, it gets a little difficult to define those boundaries. Where do you stop defining thicker oil and thin? And here's some more examples of thicker oil mixed with the rest of the oil. The bright areas, the white, silvery areas are where we would indicate thicker oil, and then the rest would be separated. And finally, just some of the challenges for oil detection using satellites. One is that we're limited by the availability of free data. We get a lot of Landsat data, Sentinel data, but it's all available for free. But we're limited to their revisit times. Also, so we need to order additional views of a particular event. We'd have to pay for additional imagery, and imagery is not cheap. So spills in open ocean usually require the purchase of commercial data because sensors are usually not imaging there. Sensors will typically image automatically over land or off the coast, but nothing in deeper ocean. So for any specialty product like that, we'll have to buy some imagery. Also, we don't perform any oil spill amount and thickness measurements because as far as we know, there aren't any good techniques for doing it. Nothing that's very accurate. But I know that there's a lot of research going on, and Oscar Garcia is conducting some of that research now. And we're assisting with the satellite data collection for that event soon. But because of the pandemic, it's also been a little difficult. And finally, differentiating marine oil spills from false positives in SAR is very tricky. So we use a lot of data, that's GIS data that's available to help us pick those out. And that is it. So just in time.
All right. Thank you, Juan. That was for your excellent presentation. You mentioned the cost, and I just want to mention that, being from a state agency, we don't have the resources to collect this data. And it's very reassuring to know that somebody is watching out for us, NOAA specifically. I'll just say you can run, but you cannot hide.
That's right. And word spreads. I mean, our reputation now precedes us because we get asked for more assistance. This is good. We get, our names getting out there, and we're happy to help in any way we can.
Yes. Well, we very much appreciate the work you do. I see we have a couple of questions that popped up there.
Yeah, we have a question. Are you using AI-assisted satellite image analysis for identification of potential oil spills and/or identification of potential spill source? Example, ship location, timestamp from AIS. If not, what is the potential for that?
Yes, certainly. The AIS data is one of the types that we use to determine whether something that we detect could be an illegal discharge. So we do have access to AIS data. And also we try to employ an algorithm developed by Oscar Garcia, which is called the textual classifier neural network algorithm that helps pick out oil slicks in SAR data. And we use it in certain areas of US waters. It's tricky to use in the Gulf of Mexico because there's so many oil seeps that get picked out as well. And same thing with Southern California, there are many natural seeps. So we don't use them generally in that area, but they can be helpful in other areas where we don't normally see oil slicks naturally.
Great. We have another question. Are the identification techniques, AI, algorithms, etc., applicable to drone imagery?
Good question. I don't know. It's something that we haven't been privy to ourselves. I expect that we will use drone data more in the near future as incidents occur inland. Right now, inland spills are hard for us to track because of resolutions of the currently available satellite data. Unless it's a really big spill, normal free data does not capture it. So we expect that drone data will be of use to us soon, but I don't have a better answer for that question. Sorry.
Okay, well, thank you, Juan. And we do have several drone talks coming up in the next couple of days, and you will see they are actively being used right here, right now.
I'm looking forward to it.
Yeah.